e to the pi I plus 1 equals 0. It's been said to be one of the most greatest equations in mathematics of all time and all that. And it makes sense because they have e and pi and I and 1 and 0. And they're all related together by one equation, and it's pretty cool. And common man 0, 0 asked me to, I guess, explain why this works. So that's what we're going to do. But first, we have to take a step back and talk about regular old complex numbers. So let's suppose we have a complex number z, and that's equal to 3 plus 4i, right? This complex number, and actually all complex numbers, are basically vectors, right? Because we can plot this 3 plus 4i on a special coordinate plane, right? Where the x-axis is the real axis, and the y-axis is the imaginary axis, right? So 3 is the real part of our complex number here, so we'll just drop a 1, 2, 3. 4 is our imaginary part, so we'll just drop a 1, 2, 3, 4i, and 3, 4, and we have a nice vector, right? And that represents our 3 plus 4i. Now with vectors, we can obviously find the magnitude of the vector and the direction, right? So magnitude we're going to call this r. And what's the magnitude? Well, simple old, yes, Pythagorean theorem. So this is equal to, square the x component, square the y component, add it together. So that's equal to the square root of 3 squared plus 4 squared. And let's see here, 3 squared 9, 4 squared 16, 9 plus 16, 25, square root of 25, that's equal to 5. Quick math. Alright, so that's a magnitude. Magnitude is 5. So our direction is basically the angle it makes with the x-axis. So our theta, we're going to call that theta. And let's see, that's equal to, let's do some trigonometry. So let's think about this. We're 4 and 3, opposite adjacent. Alright, inverse tangent. Right, inverse tangent of 4/3. Right, so that's the direction. So we took this complex number here that we rewrote. We took this complex number here that we wrote in terms of its x and y components and found its magnitude and direction. Now, here's something interesting. If we have a complex number w and we know its magnitude and direction, instead of using trigonometry to find its x and y components, we can just write it using this magnitude and direction like this. So we have complex number w, we know its magnitude and direction. We can write it as r e to the I theta, right? Where r is magnitude, theta is direction. So if we have a complex number here, 3 plus 4i, we can rewrite it in this exponential form. So we can say z is also equal to, so r is 5 e to the I, let's see, what's that there? Inverse tan of 4/3, right? So inverse tan of 4/3, right? So we rewrote it using our magnitude and direction, and that's equal to 3 plus 4i, right? So it's pretty cool. And similarly, if we have another complex number, like, I don't know, we say that maybe w1 is equal to 2e to the I pi over 3, right? It just means that we have a complex number with magnitude 2, alright? Magnitude 2 and direction pi over 3. So somewhere like, I don't know, somewhere right about here. I don't know. But you get the idea. Magnitude, direction, cool. Now, let's see here. Let's think about if we have a complex number that's equal to e to the pi I. So let's see, let's think of another letter. z1, okay? Let's see we have another complex number, and that's equal to e to the pi I. Alright? So you can see it's starting to come together. Now we can rewrite this as 1 e to the pi I. And boom, we can plug our magnitude and direction right here. This is r, r1 is r, our direction, or theta, is equal to pi. Right? R is equal to 1, theta is equal to pi. Now we can just plot this up right here. I'm trying to run out of space. We can plot this up right here. So let's think about this. So real axis, imaginary axis. So here, magnitude is 1. So at most is going to be within like the 1i range, right? Let's see, magnitude 1. So it can be anywhere in this like little circle area. Direction is pi. So it's going to be on the left. I guess the left part of the real axis is going to go 1 right here. Right? That's our vector. And let's see here. We can easily extract the horizontal, like the x and y components, right? Because our real component here, z1, let's see, that's just -1, right? And our imaginary component, well, I mean, it's not moving anywhere in the y-axis, so it's equal to 0. So we can rewrite our z1 in terms of x and y components as just -1 plus 0i. And, well, 0 times that is just 0, so that's equal to -1. Alright, z1 is equal to e to the pi. Alright guys, this is the big moment. Z1 is equal to e to the pi, and it's also equal to -1. So we can say that e to the pi I is equal to -1. And alright guys, big moment right here. E to the pi plus 1, hopefully you can see this, e to the pi plus 1 is equal to 0. And guys, we've proven it. We're Euler now. We've made the ultimate equation, the greatest mathematical equation of all time. So if you like this video, follow for more things like this, and I'll see you in the next one, wherever that is.